Now let's talk about multidimensional arrays. So in the previous video, we introduced one-dimensional arrays, and we said that if you know what a vector in mathematics is, then that's similar to a one-dimensional array. Well, now if you know what a matrix is in mathematics, you'll recognize a two-dimensional array is appearing to be the same. So just like before, we have an array name, and then everything in the array has a specific type, which is written here. But because it's a two-dimensional construct, we need to indicate somehow the number of rows and the number of columns for the array. That is, we need some way of letting the computer know how much memory to allocate for our array. And there's a couple different ways to do it, just like there were different ways before. So here's a two-dimensional table. The first row has elements 1, 2, and 3. The second row has elements 4, 5, and 6. If I want to create a two-dimensional array to store these 6 numbers, these are all type int, so I put int over here. The name of the array is sum data. And here I've specified that it has 2 rows and 3 columns, just like I wrote over here. And now I put the values in a set of curly brackets. But now what I've done is I specify the elements for each row in their own set of curly brackets. Because one of the things you need to keep in mind is that C doesn't really have a two-dimensional array construct. What we're really constructing here is an array of one-dimensional arrays. It may sound like they're the same thing, but technically they're not really quite the same. Now there are circumstances in which I could leave the curly brackets out here, but this is more the convention. And one of the benefits of specifying the internal brackets and also formatting it to look like this is it makes it easy to see the table, right? I could write all this in one big row, but then it's harder to line things up and understand how things should be. So just like before, indices start at 0. So now I have row 0 and row 1, and each of those has a column 0, a column 1, and a column 2. So these names reference the numbers that are in the array. So cells 0, 0 is the 1, and cells 1, 2 is the 6, and so forth. So here I've created an array of ints, has a 2 by 3 construct. Here's some values where I'm saying the first column represents a person's age, the second column represents a person's weight, and the third represents their height in inches. And now if I just want to print the weights, which would be column 1, because this is column 0, column 1, column 2, well then I go through and say, what are the different rows involved? So we talk about row 0, column 1, I get the 180, and row 1, column 1, I get the 175. We can have more dimensions. So now I have a 3-dimensional array. So this is an array of 2-dimensional arrays, where each of the 2-dimensional arrays consists of 1-dimensional arrays. And now if I want to print just this row within this table, that's in the two-dimensional array with index 1, that's the one-dimensional array with index 1, and then it's each of the columns within that array, all 4 of those, which go from 0 to 3, and that's how I print that. We saw, though, that when I was allocating memory for a one-dimensional array, if I specified all the values to be stored in that array at the time that I created the array, then I could leave the square brackets empty. And what happens here is now the computer will count how many numbers I've given it and give me just enough memory to store those 3 numbers. Well, with 2-dimensional arrays, I can do something similar. But the only one of the square brackets I can leave empty is the leftmost square bracket. I can't put in here 2 and then leave the 3 out. That would get a compilation error. But I can do this, which means I could come along later if I wanted and add additional rows by inserting them in here. As long as I also had 3 columns, this still would compile fine. So that means if we go back and look at this example, I could have technically left the 2 out, but I would have to specify the 3 and the 4. Many of our functions will need to operate on arrays. And so the syntax for that is this. Here's my function with a return type of double, but now what I'm doing is telling it I'm going to give it a one-dimensional array of type int. There's alternative ways of doing this, but this I think is a fairly common way of doing it, and it's at least my preferred way because it makes it more clear that I'm passing in an array of ints. However, what you have to keep in mind is that when I pass in individual ints or doubles to a function, remember we said we were passing by value, which meant that we're making a copy of the value, and so our function's not operating on the original variable. But when I pass, inside quotes, my array here, I don't make a copy of it. What I'm actually doing is passing in the address of this array, which means that my function can operate on the original array. But I'm not actually making a copy of it. And the benefit of that has to do with performance. If I have a million numbers in my array and I want a function to operate on those million numbers, I don't want to make a copy of all 1 million numbers because of how much memory it would eat up. So let's look at an example. So before we had written some code to find the max of a set of values. Let's use an array now to do that. Or excuse me, let's use a function operating on an array to do that, because we already saw how to use an array for that. So I'll say D is my array. I'm going to leave the square brackets empty. And there's a benefit to that I'll show you here in a moment. And let's say we have 24 minus 72, 0, 100, and 56. So here I have 5 numbers, and I want a function that can operate on this array. So I'm gonna write a function here that will operate on this, but I'm gonna write it in what I consider a very poor way of doing it in terms of scalability. So let's say we do this. So I say we want our function to return the value. So we'll find the max, int max, and we'll talk about what its initial value should be. So really something goes here. So as it's written now, it won't work. But then I'm going to say, or excuse me, I won't initialize here. This will be the value that gets returned. So this will really be this. So I'm going to say max equals find max. I'm going to give it the array D. And then whatever the value is that's returned, we'll print. Maximum value is %D. So up here in my code, I do this. I return an int. And we'll say find max. And what we're giving it is a one-dimensional array. So what I put here should match this. Or at least that's one way of doing it. Let's put it that way. Int D square bracket. Now we write the function. Change the curly brackets. Int max here. And we need to decide what's the initial value. When we had an example earlier, we had a bunch of grades. And because grades typically take on values greater than or equal to 0, I could set the max at a minimum value of 0, so that way I would always replace it with something larger. The problem with doing that here, it would still get the right answer in this case, but notice I have a negative number here. So what would happen if my array consists of nothing but negative numbers? Well, then if I start off with max equals 0, I'll get to the end and 0 will still be the maximum value because no negative number is greater than 0, which would be wrong. So we really need to pick a value that's smaller than everything here. Or at least, or take it back, not necessarily smaller than everything here, but such that the maximum value can actually replace it. So it has to at least be smaller than the max of the values. So I would rather do this. D sub 0. So what I'm doing is I'm going to choose 24, that is the first number in the array, as my initial value. So what will happen? Well, we'll compare to 24, which won't update the max. We'll compare to minus 72, which won't update the max. Compare to 0, which won't update the max. But then 100 is greater than 24, so it updates it. And then 56 is not greater than 100, so 100 will still be my max. What if 24 really had been the max? Well, that'd be fine because now nothing replaces it. Now, I could actually pick any of the positions in the array and this still would work. But if I, say for example, picked where the 56 is at, so this is index 0, 1, 2, 3, 4. If I put d sub 4, it would work here. But then if I were to reduce the number of elements in the array, I'd be referencing an element that doesn't exist anymore. But every array has to at least have a first element, so this will work in a more scalable fashion. For I is equal to 0, I is less than, we have 5 elements, so put 5 in there, plus plus, and we'll see in a moment there's going to be an issue with using the 5, but for right now this will work. If d sub I is greater than max, then max is equal to d sub I, and finally return whatever the max is. And it says the maximum value is 100, so it worked. So what's wrong with hard coding the 5 in here? Well, for this particular example, nothing. But what if I want to come up here and do something like this? I don't have to, I could put a number actually anywhere just to show that. Let's do this. I inserted 2 numbers, but now there's 7 numbers. So now I have to remember to go back into my function and change this. So I really want to pass that value in. So I really want to do this. Something like this. This actually is still wrong in my opinion in terms of scalability. But if I go with this, I can do this, int length, put in the length there, which means now I need to change this to this. And now it should work. And to demonstrate it works, let's actually make the max be at the end. To show it's getting that far is what I'm getting at. And there it is. So now what's the problem with this? Well, I would say this is better than the previous version because I could reuse this function if I want to, but I still have to remember to fix this. So it turns out there is a way to get the number of elements in the array. So let's see how to do that. So let's do this. So size of is an operator, so technically I don't need the parentheses here in some cases. In this case I won't need it, but in some cases I would, so I just always put it. But it's not technically a function, but it has a type. And so on my computer, size of returns something of type unsigned long. What I'm saying is this. And we haven't really talked about types much to know what this means. But unsigned long is mapped to a type on my computer. It could be on different computers. You could have different amounts, but this is fairly common. But it's mapped to something called this, size underscore t. And so to print this, if I'm using unsigned long, I can say %lu. But then in C99, and it turns out that this actually will work here as well, on my computer at least, But in C99, they introduced this, so you would use ZU, which would be more portable. So let's go with that. And let's see what this actually does. And then I'm going to put in D sub 0. I'll explain what these are doing after we see what values we get. So this right here returned 28, and this returned 4. So what does that mean? Well, if we look at the second one, I'm saying what's the size of D0? This right here. What size of returns is how many bytes of memory this consumes or was allocated for it, which in this case is 4. When I say size of D, for the way this array is created, there's 7 numbers here. Each of these consumes 4 bytes of memory, so 7 times 4 is 28. So how do we use that? Well, then I can do something like this. So we'll use size T, and one reason you do this is to get a really large integer, to make sure that if your array was really big, the number of elements doesn't exceed the variable that can store the size of it. So we'll go with this, but in this case I could use int actually. So I'm going to say length, and then we'll put in these values: size of D divided by size of D sub 0. And we don't need this anymore. And so what this is take the 28, which is the total amount of memory, and divide it by the amount of memory for each number in the array, which is 4. So 28 divided by 4 tells me there's 7 numbers here. And it works. So now if I want to do something like this, it just adjusted to itself. So this is scalable. I can change the numbers here that are stored in the array and still have my program work if I just recompile it. So I don't have to track down every place I hard-coded a 5 or a 7 or whatever. I just add or remove numbers and things just sort of magically work. Oops, need to recompile. So now 24 is the biggest number. So I would argue this is a much more scalable approach than what I had before. So we did pass in length. So if I'm going to do this, if I at least want to keep it consistent, then I probably should do this. What I had obviously works fine. And I've never used an array that was bigger than what I could store in an int in terms of number of elements, but it is possible. And so then you could argue then I should be doing this. And it all works. So then you might ask the question, so why would I pass in the length since you told me I can just get the length up above? Or I mean, I can get the length by using size of on the array. And here I'm passing in the array, right? Well, let's try that and see what happens. And I'll put this so it's clear where we're at. Recompile. Uh-oh, what happened? It's giving me a warning because it realizes I'm actually making a mistake, or at least it thinks I am. Here's the problem. We got a warning, but it did compile, so let's run it and see what happens. It says inside 8 instead of 3 times 4, which is 12. Remember, I said over here that I don't actually pass a copy of the array. I pass the address of the array to the function. And on my computer, addresses use 8 bytes of memory. So really all we said was, how big is an address on my computer, which is 8. So if I come up here and add numbers, I still got the correct max, but it still always says size of D down here is 8. Because I simply told the function that here's where the beginning of the array is, at where the 24 is stored. So I still need to give it the number of elements in the array so that way it can deal with it. So I can't do this down here. All right? And now it works without a warning. So there are occasions where warnings are false alarms, but you should assume in most cases that the compiler knows more about programming than you. So if it's giving you a warning, you should at least investigate and see what the issue is. All right?